Tausin, you can read his biodata.
Yes, sir. Yes. Hello everyone. Today we are delighted to have Dr. Anoop Kunchukuttan amongst us. Dr. Anoop is a principal applied researcher in the Azure AI code team at Microsoft India, Hyderabad. He received his PhD from IIT Bombay under the guidance of Professor Pushpak Bhattacharya. He works broadly in natural language processing and machine learning. His research spans multilingual learning, post-training and evaluation of large language models, reasoning in LLMs, representation learning, and machine translation. Dr. Anoop has been a driving force in building software and resources for Indian languages, contributing extensively to open source projects through CFIELD and AI for Bharat, as well as through his work at Microsoft. We are truly excited to have him with us today. Dr. Anoop, over to you.
Yeah, thanks, Tasin, for the kind introduction. Thanks, sir, for the kind invitation to uh, talk to the class. This is always good to come and talk to the class. And I suppose everyone is sitting most of you are sitting in the classroom, maybe only a few online. Is that
Yes,
so?
some online, some offline.
Okay. Okay, cool. Yeah, so let's get started. Uh, so today I'll talk about. So this is in sort of continuation of the course that you have on deep learning for NLP, and I'll talk about a important topic, which is language modeling and sequence to sequence modeling. And these two areas have sort of gained a lot of uh, importance with the advent of deep learning. So let's just get started. I'll just share my screen. Give me a second.
मी काय बोलतीये साऊंड
Mm. Just a second. Yeah, let me know if you can see my screen.
Online, yes, we are able to see. Hemant, can you please confirm if the slides are visible in the class?
Yeah, slides are visible in the class.
Okay. So sir is audible in the class, right?
Yeah.
Okay. Yeah.
Okay. Then
Please
great. Yeah.
continue.
Okay, let's get started. Okay. Cool. So let's start with this topic. So uh, we will first kind of understand what these topics are. I mean, the way we'll go about it is okay. We'll understand what language modeling is, and then how we do it uh, in the deep learning framework, and also have a perspective on how it was done in the past, right? So let's see. Okay, so what is language modeling? So it's a very fundamental task in NLP. And to explain very simply, it's about predicting, say, a word given the previous words in the context, in some context, right? So in the example, couple of examples here. So the first example is where, okay, the capital of Maharashtra is some blank, right? So you have to predict that word given the previous context. That is classical language modeling. You can frame alternative language modeling problems also. For example, a missing word, right? So this is what uh, you say the capital of something is Mumbai, right? So you have to predict that something X. This can be something like a masked language modeling problem. So you're masking a few words and asking the model to predict it. Okay, but when it comes to language modeling, the classical understanding is prediction of a word given the previous context. But there are new variants that have come up in um, recent years with different kinds of neural models, right? Okay, so language modeling is essentially the ability to predict words, and it's a sign of language skill. So this is very important, and it is at the core of many NLP applications in the old statistical NLP world, but also for current deep learning based NLP approaches as well, right? So what was traditionally done is what are called n-gram language models, and what we do today is neural language modeling. So we'll go over both of them. But just to put into perspective how important language modeling is, I'll just take a few quotes from Ilya Sutskever. So, Ilya Sutskever is was the chief scientist at OpenAI, responsible for the development of GPT-3, and he has a lot of previous contributions also. So he's the first paper that really showed the uh, capabilities of deep learning, AlexNet paper. So Ilya is an author on that, as well as on sequence to sequence learning, which we'll talk about today. So one of the most important papers is from Ilya, right? So he has a perspective on language modeling. And today, of course, this is the core skill, right? So with large language models, the name itself says, right? At the base of all the NLP today are language models, large language models, right? So what does it? Why is this task important, right? So just a few quotes from one of his interviews. So predicting the next token well means that you understand the underlying reality that led to the creation of that token, right? So if you are training on massive amounts of text, just this learning this next token prediction, you need to learn a lot of things about the world to be able to do that in a for a very complex problem, right? The task may look very simple. It's just predicting the next token, but uh, just to do that uh, needs a lot of knowledge, right? So people have thoughts and they have feelings and then they have ideas and they do things in certain ways, all of which can be deduced from next word prediction. Okay, and then prediction is compression. This is important. This is the core of most machine learning methods. All of machine learning is compression, right? So you're taking a bunch of data and then you're building a model. The model is a compressed version of the data. So now to predict the data, to compress it well, you need to understand more and more about the world and that produce the data. Right? So the more you can compress and reconstruct, the better you understand the data. Right? So that's the core of language modeling. So with a very simple unsupervised task, no supervision required. Right? I mean, all you have is text data, which you can get in abundance for many languages. You predict the next word given the previous context, right? So with that very simple mechanism, today's large language models have made massive progress. And so this is like a very core and important topic for us to understand. So let's formalize what a language modeling task is. Uh, and you can put it this way, right? So given a sequence of words, say x1 to x2, x3 to xi, uh, what is the probability of the next word, xi plus 1, given this previous context? And that is essentially what we want to learn with the language modeling task. Okay? So taking the previous example, the capital of Maharashtra is, and then there are many possibilities, many words. The space is, let's say, for the sake of simplicity, the entire vocabulary of the language. Right? So each word can have a probability, right? And so that's the distribution you want to learn. Right? And if you can assign distributions to a word given its context, then you can also assign a probability to a sentence, although the term itself, probability of a sentence, is kind of a difficult to define or comprehend what it means. But you can do that, right? Using the chain rule, and we'll come to that. So, okay, how do you compute these probability distributions? So traditionally with statistical NLP, the way you would do it is what we call n-gram language modeling. And the idea is very simple. So if you want to compute the probability of a word given a context, say the capital of, there are 3 words in that context. So then you take a large corpus of sentences, and then you compute these statistics, right? So the number of times this sequence, the capital of occurred, and the number of times the capital of followed by the word W occurred, right? So the ratio of the two is essentially the probability of W given the capital of, right? So it's the simple frequentist approach to computing this distribution. Now, what are the problems here? Uh, so, well, before you understand the context, so problem, let's see how this kind of can be uh, computed, right? I mean, in a more general sense. Right? So probability of, if you have the probability of x1 to xi plus 1, then we can by chain rule write probability of xi plus 1 given the previous context, and then into the previous context, right? Now, this is not easy to compute, right? So if you imagine, if you had to compute this for a very long sequence of say 10 words, then you would have to have the count of this whole sequence of 10 words. How many times does it occur in the corpus? Now, that is not going to occur too much in the corpus. It's a very sparse event. You might have such a sequence of 10 words only once if the context is 10 words long, right? So to make the problem simple, we say that, okay, the word depends on only the previous word or the previous two words. So if you say that the word depends on only the previous word, that's a bigram language model. If you say that the word depends on the previous two words, that's a trigram language model, right? So you make these independence assumptions. And then with the help of this independence assumption, the Markov assumption, and the chain rule, you can then write down the probability of the entire word in terms of probability of the bigrams or trigrams or whatever n-grams you choose, right? So, so now you converted this unbounded context, simplified you have made an approximation. You said that, okay, I'll restrict myself to bigrams or trigrams or n-grams. Mostly you don't go beyond like 4 or 5 n-grams. In the worst case, maybe 7, 8, but that's it, right? And so what are we doing? What is your probability distribution? So essentially it's a huge table, right? So you have a probability of a word given context of say if it's trigram, then all possible trigrams in the corpus that you have seen. That's your probability distribution. Of course, but no matter what you do, all trigrams are not going to be seen. So you have, what if some trigram does not occur in the corpus? You don't have enough of a value for it, but you have to give some value, right? And that's where a lot of the work in classical n-gram language modeling occurs, to sort of smoothen this distribution, do some interpolation to give some probability distribution to these missing events, uh, or rare, or even for rare events, right? So that we can have a more smoother distribution. All words have some distribution and they're still representative of the actual underlying distribution. Okay, so you can see the major issues with n-gram language model. Sparsity is an issue. Storage is an issue because you need a really large lookup table of probabilities, and you can only work with limited context. Beyond a few n-grams, the storage and the sparsity issues really uh, come out, and that's not then okay. You can do only like local context modeling. You cannot do long distance context modeling, which might be important for certain problems, right? So if you have a long sentence, there are clausal dependencies, or if you want to do the document level, uh, how the topics are flowing through the document, those cannot be done with n-gram language modeling. So how do we address this? And and we'll see how neural models can help address this through a series of works that have done this, right? So the first of these was the feed-forward based neural network based LM. This is work in around 2003 from Yoshua Bengio's group, and what they try to do is so instead of this is still fixed context, right? So you have to fix the n-gram size, and you have a neural network where, say, if you have 4-gram an n-gram network, so n minus 1 words as are the input, and the task is to predict the n plus 1th word. So you have a feed forward layer and followed by a for softmax, which will convert the feed forwards output to a probability distribution. So the input X sort of going through a feed forward layer, then to an output layer, and then this makes it the softmax makes it a probability distribution. So you'll get a probability for every word. So that is a valid LM. But what did we gain here? You still have a bounded context, right? You still cannot do an infinite context. Well, what we gain here is that we are using these uh, for these words. There are some embeddings. There are some vector representations for each of the words, right? Now that gives us a certain power which we did not have previously. When we are doing n-gram language modeling, whether you say house or home, they're two totally different words. There is no relationship between the two, right? But when it comes to a neural network, every word is represented by some vector, and the vector similarities capture the similarities between the concepts, right? So there is that sparsity issue is reduced. So even if you don't have not seen, say, house in your corpus, but you have seen home, you have some sort of distribution to work with. That's what you gain from using a language model here. Sorry, a neural network here. Also, the model becomes much smaller, right? Instead of having a gigantic table of probability distribution, all you have is the parameters of the network. So that's your model. And this is fixed. So no matter how large the corpus, the network size is fixed. Whereas if the larger your model gets, there is a chance that you'll see more and more n-grams in your corpus, and your model, which is essentially your large table, becomes larger, right? So with a feed-forward network based LM, you can sort of have a bound on the size of your model. Okay. Right. So what do we ideally want out of a language model? So one, language modeling should not run into sparsity issues as the context size increases. Now, distributed representations can help. We saw that. And so words which are similar will have similar representations. You can maybe have an approximate representation for missing concepts and so on. Also, there is the ability to capture long distance dependency effects. That is, can you do unbounded context? Right? So far, you are looking at only a context of maybe a few n grams, 3 grams, 4 grams, 5 grams, and so on. But can you have a really almost an unbounded context? So that's what we'll see next. At this point, if you have any questions, I'll just monitor the channel to see if there are any questions. Suppose there's nothing at this point. Yeah, just feel free to put out any questions on the channel and I'll just monitor it in between.
Yeah, please ask any questions.
Yeah.
From the class, offline, online. You can put questions in the chat box also.
Yeah.
Or if you have a question from the class, you tell this to Hemant or Pallavi.
So looks like chat is not available. At least that's what I see here. Maybe I'm not able to, yeah. So yeah, then you can just raise your hand and ask questions.
Yeah.
Okay, if there's nothing, I'll just go ahead. So the key thing to remember is, we need a way to sort of address sparsity and have an unbounded context. And here we start with our next approach, which is recurrent neural network, which is based on two key ideas. Okay, now, the first idea is, okay, now how do we represent an infinite context? So one way to think of it is, okay, can I summarize all the context information into one single vector? Okay, so essentially you have a function f which takes all the previous words and then gives you some vector c of xi, which is sort of the context representation for the current word. And therefore your problem sort of now boils down to modeling probability of xi, the current word, given the context vector for that word. Okay. Now I'll see how do we get this context vector. Okay. So in the case of an n-gram lookup, this function f is essentially this big table, right? But for RNN, we don't want to keep this large table, and we don't even want to be bounded by, say, 5 grams or something, right? So we want as large a context as possible, whatever the size of the data. So how do we do that? So the next idea is recursion. So if you define the context in terms of a word at position I, in terms of the context at position I minus 1, then that way we can recursively define the context, right? So here it is. So the function is essentially, c of xi is a function of c of xi minus 1 xi. That's all. And then you just need two inputs to construct the context vector of the previous step and the current input. So the context vector, you can also call it the state or the hidden state or the contextual representation. And now the way you can implement it is a simple couple of linear layers. So say one linear transformation applied to the previous context vector, and then one linear transformation applied to the current input, and of course the bias term. Then this, and then a nonlinear activation, sigmoid activation or something, right? That gives you the current context. So this is sort of like a feed-forward network, but it's not just the input, but also the context from the previous time step that is also feeding as input. So what have we achieved here? Now, if you want to compute the output for a current layer, you only need the summary vector, which is the context of the state vector, and the current input. So recursion has sort of helped us to uh, compress all the information from all the previous states into a single vector. And once you have represented the context, now, as I said, like you can now generate the output at this state, at this point of time, by applying another linear transformation. Okay, and that will give you the output representation activation at that point. And then if you want to then you, of course, you want to convert it into a probability distribution. So now you can apply a softmax on this output. So now at time step O1, what you have is probability of yi given the context of xi, right? So the context x0, x1, cx1, which is a combination of cx0 and x1. And then to that you apply the linear transformation and then take its probability. You do this after you have generated this output. Then at the next time step, you will again now you take the previous context C of x1, apply the context transformation WC. To the input, you of course apply WX and then do like the linear transformation. To that, you apply the output transformation, right? And then again apply a softmax. So at every time step, you are only dependent on this context vector. So that is the key point to remember here. So of course, there is only a single set of parameters. It's not like you have a different set of parameters at every time step. No, the parameters are fixed. So it's the time invariant. So the parameters are fixed. It's just that the context that is coming in at every time step and the inputs that are coming in, they will change. So no matter how big the sequence length, the compute effort is the same. That's the key idea behind the RNN. Now we'll delve into the details of how do we train RNNs and all. But before that, let's understand like what are the kind of problems which we can solve using RNNs. So a lot of the problems that an RNN can solve, we can put them under the category of sequence labeling tasks. So what is a sequence labeling task? So you can see here as an example, you have an input sequence x1 to xn, and you have an output sequence of the same length y1, y2 to yn. So the input sequence and the output sequence have the same length, but they can be variable. Some sequences can be say 5 of length 5, some can be 5, 10, but the input and output sequence must have the same length. Outputs have categorical labels. They're not real valued labels. They have to be from a finite set of labels. And the output the assumption is that the output at any time step typically depends on its neighboring output labels and the input labels from the previous step. So that and one example of that is part of speech tagging. So you have words, and then every word has a label with it, which is the part of speech. Right? So the number of output labels is equal to the number of input tokens. So for these kind of problems, sequence labeling is a very powerful approach. We'll see more problems, but this is like the kind of formulation of a sequence labeling task. Now, how do we do a language modeling with a sequence labeling task, or how can you see sequence labeling as a language modeling as a sequence labeling task? So you can think of it this way, right? So if you have a input sentence, your task is to predict the next word at every time step. So the input is the current word and the output is the next word. Right? So you can kind of think of it as shifting the sequence by one time step on the output side. And that's how you achieve modeling, looking at language modeling as a sequence labeling task. Now you might ask, of course, but don't you need a finite set of categorical labels? And vocabulary can be unbounded. So that is an issue. Typically, the simple way to approach this is to bound your vocabulary. You take only see a finite set of top k vocabulary items. That's what we used to do earlier. Subsequently, people came up with sub-word vocabularies. We'll talk about that maybe next session. But just to give you a hint that these problems can be surmounted. Okay. Now, how do you train a language model? So the input is a large monolingual corpus. Okay, and where every example is essentially a sequence of words. And now at every time step, you have to predict the distribution of the next word given the previous words. So what is the loss function you would use? So one way to look at this, just maximize the likelihood. So probability of uh, the negative log probability of the uh, current word. Say the at time step I, the word is L. So maximize this probability. So that's the standard training. And another way to look at the same objective, the likelihood objective. So maximizing the likelihood or the negative likelihood is equivalent to minimizing the cross entropy between the actual distribution and the predicted distribution. So what is the actual distribution? So given a at any timestamp I, what is the actual distribution? The actual distribution is that only one token is one, has probability one, the one that you are seeing in the corpus. Everything else is zero. So that's probability summing up to one. And then there is a probability distribution that you're actually learning. So if you learn a distribution between a cross entropy between the two, so that is like overall the vocabulary items, log of the predicted distribution, and the true distribution, which is the left term, right? ZI with subscript W. So this will become one only for L, right? So, and therefore it boils down to maximum likelihood. Okay, so if you see the term cross entropy and likelihood, they are equivalent. I mean, training for either objective is equivalent. So this for a single time step. If you average it over the entire example or at all time steps, that is the loss for the entire sequence. And then if you average it over the entire corpus, that's the loss over the entire corpus. And that's what you are kind of minimizing while training using a C gradient descent. Now, how do we learn these parameters? How does the actual optimization happen, right? So if it's a feed-forward network, you do back propagation. But now there is also a time element involved. So how do we do that? We'll come to that later. So before training, let's go over, okay, well, suppose you have trained the model. So you have learned all these probability distributions, all the parameters of the network. And now let's put it to some use. So to what use can you put a language model in? First of all, how do you evaluate the quality of a language model? How good is it? So obviously, you will evaluate it by its ability to predict the next word given a context. Okay, so which is essentially evaluate the probability of a test set of sentences. So whichever model assigns a higher probability to a given test set, which are like real world usage of sentences. So whatever model gives the higher probability, that is a better language model. So that's the way you would compare different language models. If you have different techniques of coming up with training language models, so you would compute its probability on a standard set of sentences, and that defines which one is better. So over the years, there are many standard test sets that have been defined: Pentry Bank, billion word corpus, Wikitext, etc., which are standard benchmarks that are used. Okay. So yeah, so the probability, one term you will always hear is language model perplexity. Okay, so it's another way of looking at the likelihood or the cross entropy. So it's just a more readable version, I would say, of reading entropy. So it's essentially the cross entropy exponentiated. Sometimes it is 10 raised to the cross entropy also, right? So it's a more readable number. And what you generally want is lower cross entropy or lower perplexity, right? So if you and in this case, the training objective and the evaluation objective are match each other, right? I mean, if you're maximizing probability or minimizing cross entropy, it's as good as trying to lower the perplexity. So you can just track perplexity to see how good your language model is. And this is some examples from some previous work as to how beneficial RNNs are, right? So what you see here is, okay, the first row is a n-gram language model, a 5-gram language model with Nezarny interpolations. As I said, like the n-gram models use a lot of smoothing techniques. So this is one of them, and achieved a perplexity of 67.6. When it comes to RNN, uh, immediately like there is a big dip with RNN. I think the hidden state must be 1024, and LSTM, which is a variant of an RNN, you really see a big drop to 43, right? And a two-layer LSTM, even smaller, and yeah, so on. So generally, you can see that RNNs outperform in gram models and outperform by a big margin. So these are big numbers, drops in perplexity, and that's where you really see the power of neural networks. I mean, language modeling, the scene for language modeling totally changed with the advent of language models, with of the advent of neural networks. And as you see, LSTM is much better than RNN. We'll see what LSTM is again. Okay, now you have your language model, you have ways to determine which language model is better, but of what use is it? What can it do with this, right? So, of course, what you want to be able to do is generate some text. Okay, now this is a generative model, which means you have modeled the entire probability distribution, and therefore you should be able to sample. Right? So you have the probability distribution of probability of the next word given the previous context. So if you have that distribution, you should be able to generate a new text, right? So if you have a prefix, the capital of Maharashtra, you have a probability distribution. Say probability of Mumbai is zero point 0.8, given this context, Bihar is zero point 0.1, which is natural. This is likely to have more evidence in the corpus. Now, how do you generate the next sentence? You can either sample greedily, which means most of the times you might choose Mumbai, but there is a chance you might choose Bihar and Chennai and so on. Right? And if you just do some of this kind of sampling, you can generate these kind of texts even with a RNLM. So this is an character level RNLM. So the basic unit is a character trained on Shakespeare's work, and if you ask it to generate something, maybe starting with a few words, it's generating some Shakespeare like text. That's the real power and effectiveness of RNNs. And this is another example. This was generated by GPT-3. Okay. By the way, GPT-3 is not a RNN LM, it is an LM, but a different kind of LLM called transformer. And so, yeah, neural networks can have enabled the generation of this kind of very fluent text, and which is what has led to the revolution in natural language generation today. Okay, this is some visualization. I think you should look at these resources, especially on the Karpathi's uh, visualization. So here you can see that what's happening inside the neural network, right? So which neurons are getting fired. So there is a certain set of neurons, say for example, the ones in green, which get fired, which get activated when say URLs come in. And similarly, there might be some for bracket, there might be some for punctuations, there might be some for a few concepts. So which is interesting. Okay, so where are language models put to use? So if you look at search engines, they have this auto suggest feature. So that's a place where you can use language models. On your mobile keyboards, you have autocomplete features. This is somewhere where you can use language models. And language models are used in other systems, right? So many generation systems. For example, if you're doing translation, so translation is there are two things you want to do in translation. One, you want to ensure that the meaning carries over from the source to the target. So that's the work of a translation model. And second, you want to ensure that the output is fluent in the target language. So that's where the language model for the target language comes into the picture. So the final output is kind of selected based on both how a translation model scores the output as well as how a language model scores. So you get both what you call uh, the fluency and the accuracy of translation. Similarly, for speech recognition, again, speech recognition, you have to be able to convert the speech signals into output text, but then the output has to be fluent. So that's where the language model again comes in. Okay. Yes. So let's again now delve a bit more deep into more kind of tasks that RNN can do. So broadly, the kind of tasks that RNNs can solve. We can call them natural language understanding tasks, and these can either be classification tasks, which you're already familiar with, say sentiment analysis or any of these kind of class, where the output is just one out of set of classes, right? And then you have seen sequence labeling tasks, where you have a sequence and corresponding labels for each element in the sequence. Okay, now let's see some examples of such sequence labeling tasks. So we already saw part of speech tagging. Named entity recognition is another sequence labeling task, right? So here, what is the task? So given a sentence, you want to mark off certain named entities, which might be, say, people name, and then also associate some category. So PA Winken is a person, IBM is an organization, and date is also one kind of entity. So you want to mark this. Shallow parsing. So that's like, okay, you don't want to do full parse of the sentence, but just identify chunks, syntactic chunks, right? So for example, Pierre Winken is a noun phrase, will join is a verb phrase, and so on. NP chunking, well, you're interested in only in the noun phrases and not the other kind of phrases. Okay. So these are all problems which are about identifying some sequences. Now, how do you formulate this as a sequence labeling task which can be addressed by RNNs? If you see here, this is not like uh, these first two words are called person, but I can't do that with my RNN, right? I mean, there you have to have one label for every token. So how do you transform this into a problem in that setting? So that's where uh, what is called this BIO encoding is used. Beginning, inside and outside. So you can transform this example into some other notation. So for example, Pierre Winken, this is a noun phrase. Now Pierre becomes a begin uh, kind of token with the category being NP, right? So that is its category. So for this token, this is the label. For a word inside the entity, so Winken is inside, so it is I and then an NP. Something like old, which is not part of any of the labels that you want to identify, will be labeled as O, right? So this is the simple notation, BIO. And any of these problems that we saw, if you think about it, can be represented in this notation. Okay, now okay, you have learned your sequence labeling model. How do you give labels to your outputs? So that's again, like we have already kind of seen, how do you do inference? So given that you know the distribution already, you have learned that. We'll see how you do that, but assuming that you know the probability distribution. So then assigning a tag is just either you could do greedy decoding. So you can, given a word, assign the most likely tag. That's one way of doing it. Sampling is not good in this scenarios. You typically want a deterministic answer. So greedy decoding is an okay, good technique, but you can do better with something like beam search, and we'll see that again going forward. So what we talked about so far was how do you do sequence labeling tasks? So where you have one output for every token, but can you use it for classification of entire sequences, right? So for example, sentiment classification, hate speech detection. Uh, well, we have representations, state representations for every token. How can I use that for a representation for the entire sentence? So what we can do is, okay, take the state representations, the RNN encoder's outputs at every time step, and then convert it to a single vector for the sentence. So this can be done, say, by a mean pooling, which is just averaging of all these vectors, or max pooling, where for each vector at every uh, dimension, you pick the highest value. That's max pooling, or last state pooling. Just take C3, right? Because since this is an RNN, the last vector can be considered to be a summary of the entire vector. It's in the entire history, right? That's by definition. So you can use any of these methods to convert your sequence to a single uh, vector. And now you can apply a classification layer on top, and you have an output label, say a positive sentiment, negative sentiment, or neutral, and then train a classifier. Okay. Okay, any questions at this point? Yeah, just please feel free to ask any questions if there's something that I should elaborate on. Okay. Okay, now let's then look at, so we saw all these tasks, but how do we sort of train models for these tasks, right? And let's look at the concept of language model pre-training. So one way to kind of train these models is, okay, say if you wanted to do sentiment analysis, you will collect a lot of sentiment analysis data, take a RNN from scratch, initialized with some random initialization, and then fine tune your sentiment analysis task data on the RNN network. Then that will be your network for solving sentiment classification. But is that really optimal? Uh, One, because your dataset might be small, right? And so it might not have enough training data for this particular task. And solving sentiment is not only about solving sentiment, but also understanding the language. Now, you cannot bring all the data for the entire language for this tiny problem, right? Uh, so what is the solution, right? So can we, and the answer is like, uh, can we uh, separate the problem into two parts? One is learning something about the language, and second is learning something about the task. So the first part, just learning something about language, uh, is language modeling essentially, right? So, so can you do this, right? So can you take a lot of text and just do language modeling on that? We already saw how do you train a RNN encoder, right? RNN model, right? So you just train a lot of use a lot of data just to train the RNN. That with that your model knows about the language. Then okay, you change the heads. The current heads are kind of the vocabulary of the language, but you change the heads. Now you use the heads which are relevant for your task. Maybe say sentiment analysis. You'll have heads for 3 labels, and then fine tune the network on just your task specific data. So the model now already knows something about language, and this is a one-time activity. You train it for a language, it's there, and then you can fine tune it for any number of tasks. So the first model is what you do first is pre-training, which is learning language specific knowledge, and then secondly, you're fine tuning it for a particular task. This is an important concept. Uh, and one that has the idea that you can pre-train and then fine tune has sort of been as been something that was not there earlier at all with statistical NLP, and that is a concept that is now very central to all the deep learning based NLP that we're doing. Yeah, and so there are many models like ELMO, ULM, FIT, which are RNN based pre-training ones. There are many other pre-training ones today based on the networks that we are using these days. Okay. So we saw one kind of task, which is this sequence labeling task. The other kind of task which we need to look at today is sequence to sequence task. Okay. So here, how is it different from sequence labeling? So the major difference is that input and output sequence are decoupled. They can have different lengths. So there is no one-to-one mapping between the input sequence element and the output sequence element. And many NLP tasks are of this sort. The majority of the ones that really matter, the end tasks, are all sequence to sequence tasks. Say machine translation, right? So number of input words in English and the number of output words in Hindi will be very different. If you do summarization, the number of of course, the length of the input document is much larger than the output summary. So these can be solved by conditional RNNs. So we'll see how RNNs can be modified to solve sequence to sequence problems. But I hope the task is understood to you, and a lot of interesting tasks that we want to address are actually sequence to sequence tasks. Okay, now that we have understood what RNNs are and what kind of tasks can we solve with RNNs and gone through examples, their inference and so on, let's spend some time now on like how they're trained. Uh, and here I'll just give you like a high level overview of the algorithm that is used, which is backpropagation through time. And so this is backpropagation modified and through time because you have to, during training, address all the time steps. Time is essentially the sequence length, right? So how do you account for that? That's what is the modification that the backpropagation through time does. So at any time step, the probability is this, right? The log of the probability distribution for the term L given the previous context. And we already saw this. We average over the time steps for an example. Now we have to compute the gradient for an entire sequence, right? So the gradient for the loss is essentially the summation of loss over each time step. And the model parameters are everything in the network, all the weight matrices for the input, context, output, biases, etc., everything. Now, okay, now let's look at this example. I'll just give you a high-level overview. Don't want to get into a lot of details, but just to give you the motivation of how this works, but you can go ahead and look at the details later also. So yeah, so if you want to do the loss at time step I uh, and differentiate it with respect to say the output matrix, that's easy because the output, this is directly a function of the output matrix. Loss is, this is the last thing that is applied, right? So that is directly a function. But if you have to kind of differentiate it with respect to the weight matrices for the context, now there is an indirect relationship because the loss is a function of the uh, context, and the context is a function of the uh, parameters for the context, WC, right? So we have to apply the chain rule. And since it is multivariate, uh, so you have to, there are two variables here. Nothing, I'll elaborate this on the next slide. So if you have, say, now here you have a multivariate kind of chain rule situation because you have to differentiate the context with respect to the parameters, and there are two variables here. Both the previous context is also now sort of something that comes into the picture, and that's where this gets more complicated compared to standard backpropagation. So differentiating the current context leads to two terms, one of which uh, results in this daba of ci minus 1, which is for the previous time step, the gradient for the previous time steps context. And this is where things get messy. I'll just quickly run through and tell you what the issue is. Okay, so if you just kind of, what happens is if you unroll this, right? So what you saw is, yeah, dab of Ci. If you just expand it, you get dab of Ci minus 1 given WC, right? So you can see that there is already some sort of recurrence happening. So you have to unroll this again, right? So next, if you expand this, you'll get Ci minus 1, Ci minus 2. And then you can see that there is a multiplication happening, right? Into Ci minus 1 into Ci minus 2. And that's where the real trouble starts. So yeah, so Ci is sort of a combination of Ci by Ck, right? And if you expand this, this will be some sort of multiplication of Ci by Ck will be a multiplication of Ci by Ci minus 1, Ci minus 1 given Ci by minus 2, and so on. So it's a sort of multiplication of many of these gradient terms, and that is trouble because what happens is you're multiplying a lot of these terms in order to compute the gradient. And if these terms are very small, then you have a problem. Okay, so, and you can show this, you can bound this and show that, say, if this term is very small and it's less than 1, then your gradients will go to 0. Sorry. Yeah. Okay. Yeah, so you have this entire set of multiplication terms, which are gradients. And then if you multiply all these gradients, and if each of them is, say, less than 1, then if you multiply them over as the sequence length increases, this will kind of go to 0. And therefore, what happens is the gradient signal going back to the initial terms in the sequence will be very less, right? So they will hardly get updated. Trading will be very slow. There will be no progress, and so on. On the other hand, if this term becomes very large, if any of these terms become very large, then your gradient can explode. It can become very large, and then your trading is really unstable. Again, you will not converge. So these are a couple of big problems with the backpropagation with the BPTT algorithm. And yeah, exploding gradient, one way to solve it is to sort of, it's kind of a heuristic. You can clip the gradient before parameter updates. So you don't allow the gradient to become larger than a certain value. And therefore, like you can sort of help avoid overflow errors and things like that. But you still have to solve the vanishing gradient problem. Okay. So what is the main problem here, right? I mean, the problem was that, and this is sort of a graphical illustration of the problem. So you have all these gradient terms and you multiply all of them, right? So Ci is impacted by Ck through Ck plus 1, Ci minus 1, and so on, right? So there is no direct connection between Ck directly impacting Ci. And therefore, its impact is very low because the gradients have to flow all the way back from Ci to Ck. And by the time it flows back, we have this, and the values are small, there will be no, there will be no update, right? So, okay, why do we have this indirect connection? Will that happen because we chose a recursive solution? What if we can, each of these can directly impact Ci? Well, that was the first solution we proposed, right? The feed-forward solution was that everything every word in the context directly helps predicting the output. But we know that that will not work because you cannot handle unbounded context. So is there some solution between the two, right? And that's where, well, again, at a very high level, the intuition is, okay, if I want to do Ci, and maybe it depends a little bit on Ci minus 1, a little bit on Ci minus 2. So can I have some scaling factor, right? So maybe it can be binary switch. Okay, it depends only on Ci minus 1 and only on Ci minus 2, doesn't depend on Ci minus 1. So you use only one of these words for modeling. That's, of course, you don't really know. So can you sort of learn that also from the data and have some sort of a smooth switch? Right? So which means you give some weight to Ci minus 1, some weight to Ci minus 2. That is a high level intuition. And so, yeah, all of these directly impact Ci, all of the previous gradients, but in different ratios depending upon how important they are. So these are like switches. These lambdas are like switches, some values that you multiply Ck with to select how much of an impact they have on Ci. So this kind of is a um, diagram to kind of give you the concept, but its implementation is more involved. That's what the LSTM or the long short-term memory is all about. It applies the same idea. It's a special kind of RNN cell, but it has all these essentially all these kind of lambdas, which are switches that control how much of Ck plus 1 and Ci minus 1 impact Ci. And that's achieved through a bunch of gates, right? So these switches for gate. So you have the input coming in xt, and then you have a bunch of these gates. So the forget gate, which decides how much of the previous context should you keep. Then there is an input gate, which decides how much of the input should you consider. And there's an output gate, which decides how much of the output you should consider it. So, well, so essentially, yeah, these are the formulas for each of these operations. But broadly, yeah, the idea is that, okay, through this sequence of gates, you have this kind of a direct connection where maybe Ct minus 1 can directly pass through and impact the last sequence element also. Maybe it is discounted a bit using these switches which are marked in X or impacted by the input coming at this point, but there is still some sort of a soft connection between CT-1 and the subsequent states. And that's what LSTMs help achieve, this kind of a direct path between in elements across the sequence. So that's the LSTM, and that helps to sort of solve the vanishing gradient problem. And yeah, then there are variants of RNNs and LSTMs. Especially, we should talk about the bidirectional RNN. So far we have only been talking about LSTMs going from, say, in one direction, right? So you see the next, you predict the next word given all the previous words. But in some applications, you need to see the words, the next words also to be able to predict. That's more useful. Like more information is always useful. And sometimes you have the entire sentence, so why not look ahead also? So to kind of model that, we have bidirectional RNNs, which is just two RNNs, one going from left to right in the text and one going from right to left in the text. So you have two state vectors at any point of time, and you concatenate the two, and then you have a bidirectional context vector. That's all. It's very simple. Then you can, so far we talked about RNNs which had only one layer, but you can stack together many layers. So the more layers you have, the more complexity you can, the more analysis you could do, right? Every layer builds upon the representation of the previous layer and you get more deeper representations. GRUs, etc., are variants of LSTM, better flow of information and so on. So, okay, so that's okay. Essentially, what we had for LSTMs. So with this, we looked at this kind of architectures for sequence labeling kind of problems, where we looked at RNNs and their variants, LSTMs, which can help solve some of the problems with learning RNNs. So the next topic, we can take a break here, take some questions before moving to the next topic, which is encoder decoder models. Okay, so just take a pause, and if you have any questions, I can take them. Yes, Hemant. If you're saying something, you are on mute.
Hemant, you're saying something?
I guess that happened by mistake. You can go ahead, still ask some question.
So there's a question posted in the online chat. So the question is, why can't we keep a minimum threshold for vanishing gradient problem, like gradient clipping for exploding gradient problem? So
No, I mean, exploding gradient problem, if it's exploding, you can cap it to some value. But what do you, for a vanishing gradient, the problem is that, okay, you're doing a series of multiplications. Now you're saying that, okay, if the value goes below a certain value, then you kind of keep a minimum value of the gradient. I don't know if someone has tried this, but I mean, either approach. I mean, even the clipping of the gradient uh, for providing for vanishing gradients is a hack. But if you have a better solution which is more elegant, then why not use it? Which is what LSTMs provide. But I don't know if someone has tried that. I mean, clipping it to some minimum value. Okay. Right. So I cannot see the chat, so I will not be able to see the questions. So yeah, someone should let me know the questions. Okay. Okay, then shall we go ahead? So I plan to also do sequence to sequence modeling today. That's the agenda. So does that sound good, sir? I'll just do sequence to sequence modeling.
Yeah, please go ahead. Yeah. Yeah, no, it's okay.
Yeah, sure. I'm quite good. Okay, so I'm back to my presentation. Fine. So yeah, so we looked at sequence labeling so far and language modeling, which is like a special case of sequence labeling. We just had a small introduction to what a sequence to sequence task is like, which is input and output can have different lengths. And that how do we solve this problem? That's what we'll look at for the rest of the talk today. And so what is used for solving these problems, what are called encoder-decoder models. So we'll see how that works. Yeah, so again, to formalize, a sequence task has an input sequence and output sequence. These can have different lengths, and the length is, of course, variable. Mm. Output is again categorical, as in the previous case. And output at any time typically depends on the neighboring outputs and input elements. So machine translation is a classic problem for this setting. And encoder decoder is the general framework for solving sequence to sequence tasks. And yeah, but there are many other problems that can be looked upon as sequence to sequence. In fact, most problems can be seen as some sort of sequence to sequence problems. So summarization, input sequence is an article, a sequence of words, and output is a summary. Question answering, input is a question, output is an answer in tree form. Dialogue, you have a previous utterance, and then you have to generate the next utterance. Transliteration. So transliteration is the problem of converting text from one script to another script, say from Devanagari to Roman. Okay, and so the input is a sequence of characters in, say, Devanagari. The output is a sequence of characters in Roman script. Grammar correction, an incorrect sentence is the input. The output is a correct sentence. Translation post-editing. So this is a problem where, okay, you have the input and an incorrect translation. Both of them are the input. And the output is the correct translation. So sometimes this is kind of a, as the name suggests, it's a post-editing step. So once you have automatically translated something, you could also have a post-editing system which can use of more information and try to correct the translation. Or sometimes the human was translated, and then maybe there are some mistakes, and translation post-editing can help improve productivity. Image labeling. So given an image, so image is also a sequence. It is a sequence of pixels, and the output is the label. So what is this image about? So here, what we are interested in modeling is probability of y given x, right? So probability of the output word sequence given the input word sequence x. Now, here is where it differs from the language modeling task, where it was about probability modeling the probability of x only, right? The input sequence only. What you can do here is this is a conditional language modeling task, you could say, right? So you have to the output sequence probability is conditioned on the input sequence or the source sentence. So in probability terms, so it's the probability of every output token yj is dependent on all the output tokens seen so far till j minus 1, but also each output token is dependent on the entire input sequence because you've already consumed the entire sequence before you start generating the output sequence. That's the way you are modeling this problem. So if you're translating, the process that you're defining is that I have read the entire input sequence and then I am starting to generate the output. Okay, this might not be true. I mean, you might be able to do chunk based translation, but but the way we are modeling it is in all these encoder decoder models, you read the entire input, then start generating the output. And so the input is always a condition. The entire input is always a condition for the output token at every time, at every time step. So if you remove this X, what you have is an RNN, right? A standard RNN, but this X is what makes the difference. Okay. So if there were no X, you could just have a RNN on the target language side. So now think about it of how do you incorporate X in the input into this. So let's say that I have a language model for the target language sequence. And since this is say an RNN, there is of course a state involved. So there is an initial state also involved, right? Now, if you can initialize the initial state um, as a representation of the source sentence, right? Just pay some attention to that. If the target RNN's initial state can be initialized to uh, some representation of the source vector, source sentence, then you are done, right? I mean, then you already have some representation of X, and then you can keep generating the target set. And that's how you have a conditional LM, right? So you have included X here in some way. Now, but then the question is, okay, how do you generate this HN, which is the last state for the source sentence? So the idea is simple. Okay, you have another RNN for the source sentence. So the source sentence RNN generates the state for the source sentence, and that is used to initialize the uh, state for the uh, target language for the output sequence. So you have two RNNs. So one is the source RNN, and the other is the target RNN, and that's what is the encoder decoder approach, right? So there's an encoder RNN for the source. There is a decoder RNN for the target. And so what we do is encode. So the way the whole process works, so the encoder will first encode the entire input sequence. So if I'm say translating this sentence, I read the book. So I process that entire sequence. A representation for the sentence H4 is generated. That is used to initialize the decoder's state. Decoder is another RNN for the target language or the target sequence. And then you start doing generation for the target language. So at every time step, you generate one word at a time, and that is a translation. And you continue doing that till some end of sentence token is generated or something like that. So, so this is the decoder. So the decoder is just another RNN, not very different. The only difference is it is initialized with the state of the source RNN. And you will train the model, of course, end to end to generate the entire output given the input sequence. So let's look more closely at what the decoder is doing at every time step. Yeah, so what the decoder is doing is it SJ minus 1, which you can see here. So that is the previous time step decoder state. And C is the state of the encoder, which is the summary with this which is what you initialized with, but you also give it at every time step. We'll come to why. Right. So at every time step, you give the previous time state of the decoder state, the source representation, and then the embedding for the previous word generation. That is typically how you model the machine translation. And then it's the standard RNN approach, right? So now you have an RNN LSTM cell which generates the next state and the output and softmax and so on, right? The key thing to remember is this C. At every time step, you are giving the source representation also. This is how it differs from the RNN approach. So the way you train it is, again, maximum likelihood. You want to maximize the probability of y given x. One thing to remember, right? I mean, so now you might wonder, okay, at every next step, what is the output that you want to give? So if you go back to this previous example, say मैंने किताब पढ़ी, that is a translation, right? But initially your model might not be generating nay, right? So whereas the gold standard says nay. So should you train on whatever the model has generated so far as per the model's parameters, or should you look at the gold label, right? If you look at the gold label, the problem is, yeah, that's the correct output, but the problem is it is different from inference time situation, test time situation, where the model might have made some errors during translation on the previous step, right? Uh, Whereas if you use the model's output during training, it will degrade the performance because initially the model is not good at all, right? So typically, what you do is feed the ground truth instead of feeding the previous model output. That's called teacher forcing. It's not optimal, but that's what works fairly well. So you always feed the give the model whatever is in your gold standard, whatever is the output at that time step. Uh, but then, as I said, there is a discrepancy between the train and test scenarios. So you can sort of do a combination of the two. So initially, when you train the model, you can sample from the ground truth or the ground truth, right? And as the training progresses, you can rely more and more on the model's predicted level because the model is now better at predicting. So it's sort of sampling with the higher probability for the ground truth initially. And then as the training progresses, your sampling schedule varies and you give more weightage to what the model is predicting. So by the end of training, the model is robust enough to handle the kind of errors that might have happened in the previous step. So this is called scheduled sampling. That's also like something that improves translation models. Okay. I had a section on decoding, but I think I'll skip this for today and jump to attention models and come back to this next time. Okay, so because that will be a better flow, right? So we looked at encoder decoder models. We saw that during decoding, when the target decoder is generating, it is always looking at the source vector also, source sentence also represented as a vector. Now, the problem here is that the entire source sentence is represented again by a single vector. Okay, so there are two problems with that. One, that's insufficient representation to capture all the complexities of the source sentence. So if you're using translation, if you're doing translation, can you look at only one vector representation of the entire source sentence to do translation? Probably not. I mean, it's a more complex problem. You need to know the words and the semantic relationships between the source words, etc., to do translation. Secondly, yeah, if you use the approach of initializing the uh, decoder with the state of the source, then after a few time steps, the source representation is kind of forgotten only. So no use of it. One workaround is what we saw that, okay, you can feed in the source representation at every time step of the decoder. That can solve the issue to some extent. But what you really want is to have more fine-grained information and not just a single vector. So yeah, this we already saw. We can feed the encoder state at each time step. That partially solves the issue, but you still have this issue of how do you provide more information and at every time step of the decoding. Okay, so how do we do that? And even better, uh, don't provide all the source information, but also only relevant source information. That's what is the next solution, which is attention mechanism. So that is again a very important uh, concept in NLP. It is again another concept that has sort of revolutionized the field. So all the pre-trained models today have attention in some form or the other today. So very key idea. So we know one thing, right? So if you have the encoder, at every time step, there is a state output from the sources encoder, right? So let's call that an annotation vector. Now, this is so you can now look at your source sentence being represented by a set of these vectors rather than a single vector. Okay, but of course you cannot feed in a set, and especially an unbounded set to the decoder at every time step. So you have to do some operation on this set of vectors and construct a new vector, which is not like you supply an average or the last state at every point, but something that is relevant at every time step. So that is the key idea behind attention, that you attend to the vector. So the key insight here is not all the annotation vectors are equally important. So for example, if you're going to generate, say, ghar on the target side during translation, what is more important is the representation of home on the source side, right? And not the other words. And so not all the source words are equally important. So okay, one way to think of it is then the context vector, the vector that you feed, source representation that you feed to the decoder, can be a weighted average of the input annotation vectors. And you give more weight to the words that are more relevant to the current prediction to be done. Okay. So that's the idea. So you give more focus or more attention to the words that are relevant at this time step for this prediction of the decoder. That's why this whole idea is called attention, because during decoding at time step I, you will decide where do I focus more. So let's look at this through an example. Okay, so we have the source sentence, say it has 4 words, so E1, E2, E3, 4, and the encoder will have some representations for that, right? Now we want to give one vector C1 as input to the decoder at time step 1. Now, what is that one vector? So earlier, the simple encoder decoder paradigm, this used to be just the last state of the encoder. Now we're seeing we'll do better. Instead of doing that, we'll just take a weighted average of all the states of the encoder. Okay. And these weights will be relevant to the current state of the decoder, whatever it has generated so far. In this case, it is at the initial state. So it will be relevant to the state S0. And depending upon that, the weights will be chosen: A11, A12, A13, and A14. And you will then end up with the context. Similarly, once you have done that, the C2 will now be different because the attention weights will be now different. A2, now this is A2 series, right? A21, A22, A23, A24. That is for time step 2. Now this attention weights will be different, and therefore the context vector will be different. Now this C2 will be sort of relevant to the fact that now you have already generated may, and the state is S1, and C2 will be a function of that. We'll take into account that. So now you are more informed. You know mane has been generated, and so ne can be the next word, right? And therefore the attention will be accordingly adjusted. And similarly, you go from time step to time step till you generate the end of the word. The key difference is now C1, C2, C3 are different at every time step, unlike in the standard encoder decoder. The question is, how do you find these attention weights? Okay. And the answer is as we always rely on in supervised training methods, let the training data decide that for you, right? So you don't know, right, for every word what is the attention to be given to every source word. All you do is model, right? So you say that there is some weight, uh, some similarity between the current state and the current and each input vector. EI is the input vector. So EI has some similarity to the current decoder state and the current output that has been generated, or the previous one to be more specific. And this is captured through a function G. And so this function G can be implemented as a simple feed-forward network or a multiple ways of doing it. But essentially, yeah, you capture the similarity of the current input with the current state of the decoder. Right? And now your attention weight, this is just the softmax operation, right? So you have this alpha ij, and if you just do a softmax over all the i's, over all the inputs, you will get a distribution, which is the attention weights. And once you get that, then we already saw that uh, the context vector at time step j for the decoder is just a weighted average over all the input vectors. Okay, so now at every time step, you can have a different representation for the source, which is relevant to what the decoder state is currently. So yeah, so the key thing is this little network called G, this little function, which will learn these weights, which will help to learn these attention weights. Note that attention weights are not parameters. Okay, they are they're computed at every time step. Okay, so now let's revisit this decoder, what the decoder does at time step t. So the only difference from the previous image is earlier it was a fixed c out here. Now it is cj, that is the context vector, depends on the time step j or j minus 1 for the decoder. And that is computed through this small attention network, which takes into consideration the previous state and the entire source and the previous output from the uh, previous time step. Right? That's the only difference. So what was a fixed C becomes Cj, and all this mechanism that the attention model does is compute this Cj. And there are different ways of doing this. So you can have a simple feed-forward network. You can have even simpler models, just a dot product between the state vector of the decoder and the encoder representation. Or you can have a scale dot product. This is what you typically use these days in many of the networks. Right? So yeah, to summarize, attention is a very general concept. I mean, and very important to deep learning, very central. And it's essentially what you're doing is associative memory read. You're looking up memory based on similarity. So you have a set of values. So in the case that we are now looking at, the set of values are the encoder's uh, attention vectors, the states of the encoder at every time step, uh, and how similar they are to the decoder state. So the decoder state is a query. So the query is matched to the encoder through a key. Now sometimes the key and the value can be the same. In the case of MT, in this network that we saw, the value and the key are same. So, but sometimes the key is like a more compressed representation of the value. And you compare the query and the key, and that's how you get the attention weights. And then you do a linear uh, combination of the values with the attention weights. So what does attention provide? This is particularly for machine translation. It sort of helps, and in general for most generation problems as well. It helps the models perform better on long sentences because now the model can attend in a more smart way, focus on for the next generation, whatever is more important on the input side. This major benefit is that word order is no longer a major issue for MT. So if you know about classical MT, one of the central problems was how do you generate output in the correct sequence? Uh, s- uh, and the input and output languages can have various, very different word orders. For example, if you're doing English to Hindi, English is a SVO language, subject verb object language, whereas Hindi is a subject object verb language. So the word order changes, and that was a major headache, getting the word order right. And most of the research on statistical MT is around how do you do good modeling for getting the right word order and getting very fluent output. Now, with attention, with all the distributed training that we can do with neural networks, fluency and attention, two big problems for MT were just gone. And that really made MT go into a different league with the advent of deep learning. Okay, so there are a bunch of other interesting approaches. But I think in interest of time, I'll not cover them, and I plan to cover them anyway. Just a note of other places where attention can be used: pointer networks, modeling coverage. I mean, sometimes coverage is interesting. Okay, have you sort of covered all the words when translating? Right. So coverage. There is work which sort of keeps track of, okay, have you given enough attention to all the words during translation and so on. Okay, yeah. So I think that's what I plan to cover today in more time. So with this today, what we have done is I looked at two kind of sequence problems, sequence labeling and sequence to sequence. Sorry, was there a question there? Okay, yeah, yeah. So just to summarize, yeah. So we looked at uh, problems of sequences today, and two kinds of problems. Sequence labeling, which is like input and output sequences have the same length. Sequence to sequence tasks, where input and output have different lengths. And to address these kind of problems, we looked at recurrent neural networks and then conditional recurrent neural networks, which are essentially encoder decoder models. And finally, attention models, uh, which sort of help to sort of help focus generation correctly on the decoder side by looking at correct parts of the input. So these are all very important concepts, and as I said in the very beginning, like language models are the core of all the work on NLP today, and these concepts are all very important there. So thank you. I think that's it for today. If there are any questions, yeah, you can ask me now, or you can also drop me a mail or something. Yeah, are there any questions in the chat?
Anything from the class or in the chat box? Looks like none, no? So extremely lucid and well-covered material. Thanks a lot, Anoop. So
Yes.
you have another class next Tuesday,
Yes,
and
sir.
where you will also kindly give an assignment, which
Yeah,
will be demonstrated end of September.
yeah, sure. So I think we can give an
Yeah.
assignment on sequence to sequence well, and also like maybe cover transformers. Do you want me to take that up as an issue?
Yeah, I think so. Yeah.
Okay.
Yeah.
Sure. Okay.
So that will be great with applications and so on.
Yes.
Okay,
sure.
class, take advantage of all these beautiful lectures. Do look at the, by the way, Anup, your slides and recording will be up on the course website. That's okay,
Yeah.
right?
Yes, sure, sir. Yeah.
So Tejamai will approach you for the slides. Not
Yeah.
Tejamai, Tausin.
Yeah, I am already talking to him. Yeah, sure.
Yeah. Thank you. The class is over.
Okay. Okay. Yeah. Thanks, everyone.